Welcome to the Convince tutorial on model verification. In this tutorial, we provide a model of the fetch and carry case study, which we shall process with the AES2FM model compiler first, and then verify using the scan statistical model checker. The first step is to run the Docker. So after you clone the overview repository, you will see that you have access to a Docker Compose image. And the first step is to make sure you have the latest version of Docker image by pulling it, and then we build it to build all the necessary prerequisites that verification requires. This will take a while. As we have done that before, we now spend this step, but imagine you had it completed. And then we can finally run the Docker, and we are ready to pass to the next step, in which we compile the models with the AES2FM tool. So we see that there is a source for a directory inside which we have the tutorials, and then inside that we have simulation and everything else that we need to run our experiments. But what we are interested in now is the ROAM model folder. So inside here, we see that there are ROAM models given by main XML manifest and various types of other files. So we use the AES2FM tool to convert the model described in a main file into an SC XML type of model. This will produce an SCXML folder full of all the SCXML automata that we need, and that represent the compilation of the model that is provided. We only need to copy the scan properties inside the SCXML folder so that we know what to verify, and we are ready to start with the verification tool. You can see the help screen for scan, in which all options are described in detail. And the first thing we shall do is to validate the model, which means just checking that the model can be correctly parsed and built by scan. Since this is successful, we can now verify the property that is provided, which is the snack on table property, saying that, predicating that eventually the position of the snack will be in position x equals 4, y equals 2, belonging to world. So how do we do that? We call scan on the SCXML folder, asking to verify the property snack on table, and we see that the property succeeds with success rate 1. So all runs succeeded, all 490 runs succeeded. The minus d 1000 means that the model has a maximum duration of 1000 time steps. This is something that we have to derive from the auto-generated global timer. We see here that the time will go from 0 to 100,000, representing milliseconds, in steps of 100 milliseconds at a time, for a total of 1000 time steps. So we can now repeat the verification steps on the other models. The main locations model is more complex than the first one, as it introduces multiple locations, and we repeat the steps as before, copying the property files, and validating the model, and finally verifying the property. Instead of verifying snack on table property, we can also just ask to verify all available properties, which in this case is still snack on table, and this works just as well. The next model introduces potential failures in the model, and these are unhandled, so they will cause the model to fail if any of these probabilistically modeled failures happen. So we expect this model to fail, but scan will be also able to tell us what is the failure percentage. Copy the property file as before, and we see that we have our full model with all of the automata. And since this verification will be a bit longer than before, on top of the previous options, we can also pass the progress fancy option, which will give real-time feedback on the outcome of the verification. And thus we have found that the success rate is 0.14, meaning 14%. So without handling failures that the task will often fail, then on the same model, we now modify the policy to try multiple times failed actions so that even if something fails, there is a chance to still repeat the action and succeed. Again, we copy the property file and we see that since the policy is more complex than before, in particular, the model will be larger and have a more node, more ASCXML automata given by the BT nodes. So we validate the model, we launch verification as before, and we see that the model almost always succeeds. Now, to study why the model fails, we want to get execution traces. Scan is able to write out execution traces using the trace function, not just output the trace, but it will also organize them by satisfaction or failure of the property. So we can ask for 100 traces. These are saved in a folder, and inside this folder we have two subfolders for failed and successful runs. And here we have all the traces which are given in a plain text CSV format, then compressed to limit the amount of space required, as these traces can get very large. So we computed traces for the version without failure handling. Now we do the same for the version of the model with failure handling, and we see that we get few failure traces and many successful traces. Now to examine these traces, we can uncompress them using a compression tool such as gzip, and then the trace is given in comma separated values, which is a type of plain text format, so we can just print it to the screen and look at it. The file is though very large, and it is not easy to examine it looking at it like this. So let's now look at execution traces using a more sophisticated tool. These are CSV traces. We can use a spreadsheet tool to open them and examine them. So let's start from failed executions, which come from the behavior tree that does not handle failures. So we just pick one, open it, and open it with a spreadsheet tool. And now we see that traces are composed by logs of events, and for each event we have the time step in which it happened. We have the origin and target automata from where the event was sent. We have the name of the event and the values that it carried. And finally, we get a trace of the current values of the ports that we are examining and that we declared in the properties file. In particular, we have the x and y coordinates of the snack and the x and y coordinates for the robot. And so we can use these to better understand what is going on by plotting them. The initial position of the robot is actually spurious, so we want to skip that first state. Then we select the columns we are interested in and exclude the first set of values. And now we can use chart tool to plot these data. We select an XY scatter plot and we adjust the data series by actually removing this one we are not interested in. So the first series is the position of the snack with X values on the G column and Y values on the H column. And the second series is the position of the robot. We need to fix the X values which are from the J column, not the G1, and Y values from the K column. So now we add the grid for the X axis just to display things more nicely. We produce the plot. Let's zoom in and we can see that while the robot starts from 0, 0 and moves first left and then down to 1, minus 1, it then stops there and it never reaches the snack in position minus 2, minus 2. And the snack never moves from its original position. So we can assume that the robot doesn't get to the location of the snack and then it never does the grasping and the task is never complete. Let's now look at a different trace. Let's look for a larger trace, which we can assume will display something different from the first one we examined. And we repeat the same operations as before. So we open it with the spreadsheet, select the snack and robot positions, exclude the first row, and insert a chart. Again, it is an XY scatter plot in which we have to manually fix the data series. We have the snack and the robot data series where we need to fix the X value column for the robot. We add the X axis. Let's zoom in. So something different is going on now. We see the robot starting from the origin position, moving down and then all the way left and reach the position of the snack. Then the snack moves instantaneously to the 0, 0 position, which is actually a sign that the grasping took place, as we assign the snack the 0, 0 position conventionally when it is grasped. And so the robot moves to the final destination. It goes all the way right and then up, but the final location should be in 4.2, and we see the robot stopping at 4.1, and the snack never leaving the 0, 0 grasping position. So we can imagine that here the robot successfully reaches the location of the snack, grasps it, goes towards its final destination with the table, but it never reaches it, so it never gets a chance to drop the snack to its goal location. And now let's go look at the different execution. We move to the model where the policy can handle failures, and we take a successful execution and we repeat the same steps as before. And here we finally see a successful complete execution. Let's zoom in and we see that as in the previous failed execution, the robot reaches the location of the snack. There is a grasping which moves the snack to the 0, 0 location, and then the robot this time actually reaches the 4, 2 location and the snack gets dropped there. So it appears to instantaneously move from 0, 0 to 4, 2, but it actually is moving from the grasping position onto the table